This mini lecture will show you how to handle road map problems such as the ones you'll see on test 4. If you haven't already, go back and take a look at the ozonolysis mini lecture because that will help you with this one. Alright, let's take a look at the kind of problem we're seeing here. The first part involves an alcohol and it's being treated with H+. So what we're looking at here is an acid catalyzed dehydration forming 3 products, presumably alkenes. Using ozonolysis, you can see that what we're getting is these ozonolysis products, and the hope is we can use these ozonolysis products to identify the alkenes that we're getting from here. Alright, well, let me show you how I would handle this particular kind of problem. In the first step, what we're going to do is we're going to react this alcohol with H+. And what that's going to do is it's going to give us 3 products. And we know what 3 products is going to give us. What we don't know is which is A, which is B, and which is C. And at the moment, we're not too concerned about that, but we will be in a little bit. So that's one product. That's our second product. And here's our third product. If you'll remember, the pattern that goes along with these dehydration reactions is that we take the OH off and we can draw a double bond out to any C that has a hydrogen on it. And since all 3 of these C's have hydrogens on them, then we can draw double bonds out to each of them. So all 3 products there are possible. What we don't know yet is which one's A, which one's B, and which one's C. Now here's how I would handle this. The first thing I would do is treat this one with ozone and see what kind of product we get. Now going back to the ozone patterns, what we see is that the double bond gets split and we put a C double bond O on the ends of where the double bond actually was. So that gives me this compound here. I'll do the same thing to this one. Again, I'm going to split this double bond. I get a double bonded oxygen there, it's a double bond O. And we get this one here. And for this one, we split it here. Now I want you to remember at the end of this double bond we have a CH2. So if we follow the same pattern, we'll put a C double bond O on this carbon and we'll put a C double bond O on the CH2 as well. So we've got a C double bond O here as well. The next thing we need to do is we need to match up these structures to the ones that we see here as products of the alkenes and ozone. What this will allow us to do is then to assign letters A, B, and C to these particular alkenes, which will help us solve our problem. Now to help us do that, what we can do is we can take these structures and see if we can write them out in the same way as they're presented here. This one is 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like it's a 9 carbon structure. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'd have a double bond O up here. That would be on the second carbon. If you want to number it, you could. And we've got a carbonyl group on 2 and another carbonyl group on the 7th one. And that's what we've got. So what we see is that A produces this particular diketone, and that matches this one down here. So these two are exactly the same. What that tells us is that this alkene is A. Now understand, this compound isn't A. A, when it reacts with ozone, forms this compound. Now this one here, I'll just try and draw that out. And we've got 1, 2, 3, 4. So that's that compound there. And you'll notice that it's a match for this one. If you just sort of flip it over, it's going to be exactly the same as that. So what that tells us is that this compound must be C, because C gives this ketoaldehyde compound, which is this one here, which is this one here as well. Now if that's A and that's C, by process of elimination, this one has to be B. Now we can already see what's going on with this. We've got A, which is given that, so we've got A, we've got C, which gave this. Now we can finish up the rest of the problem. We've got B here, and it's being reacted with BH3 and H2O2 and OH minus. Now what we know is that when the double bond reacts with this reagent, we get an OH on the least substituted carbon atom. If you'd like, you can go back to hydroboration and take a look at that mini lecture, and you'll be able to see that. So that allows us to get D. So that's D right there. Now A is this compound here. When it reacts with hydrogen and palladium, what we get is a cis hydrogenation reaction occurring, where we end up with this as our compound E. Alright, let me see if I can get a little bit more room here. I'll show you another way that E could be drawn. So we could draw it with the CH3 and the ethyl sticking up. And then we can throw the hydrogens on as well. The hydrogens from the palladium addition. You don't have to put them in though. I mean, this is if you've got these groups sticking up, then it's implied that the hydrogens would have been sticking down. So this is an okay structure for E as well.